Now that we got a little better understanding of the basics of stoichiometry, let's dig a little bit deeper. So in stoichiometry, we got the concept of the limiting reactant. When you mix multiple substances together and they cause a reaction, one of those substances may run out first. And when one of your substances runs out, the production of your product stops. So we call this substance the limiting reactant. So the limiting reactant is a chemical substance or substances in a reaction that are totally consumed during the reaction. When one of those reactants runs out, the reaction stops. And if your reaction stops, you're no longer producing product. So the limiting reactant truly determines how much product can be produced. Then if you have one reactant that is limiting, the other reactant is considered to be an excess. And we mentioned this one in the last video. We kept saying maybe oxygen was in excess, so we're not going to worry about it. Well, the reactant in excess is one that is not consumed fully by the reaction. When the reaction stops, you will have some that remains. And the excess reactant is still present because there's nothing left to react with. So that's why we say we have plenty of it. We don't have to worry about it. But either way, whether we're dealing with limiting reactant or excess reactant, the way we determine that is once again through the balanced equation. So let's say we had just an arbitrary reaction, just a general reaction. We'll do A plus B yields C. Let's give it a balanced equation. We'll say it's a 2 to 1 to 2 ratio. So the balanced equation is telling me I need 2A molecules for every 1B molecule to produce 2C molecules. So that means if I have 4 moles of A and I have twice and I need twice as much as B, that means I need to have at least 2 moles of B because it's a 2 to 1 ratio. But what if we don't have that perfect ratio? Instead of having 4 moles of A and 2 moles of B, what happened if I had 3 moles of A and 2 moles of B? Well, I don't have twice as much A molecule as I do B molecule. I have just a little bit less. So when this reaction stops, both of these substances will not be consumed completely. One will remain. And the one that is excess, or the greater quantity according to its balanced equation, will remain. So in this instance, I should still have some B left over because there was not enough A to fully consume B in the reaction. Or let's look at it just a little bit simpler. Let's go back to those hamburgers, making some hamburgers. Let's say we got 8 buns, top and bottom. We got 6 patties and 50 cheese slices to make us a little cheeseburger. So how many hamburgers with this resource amount could I make? Well, if I got 8 buns, 6 patties, and 50 slices, how many hamburgers I can make is determined by which ingredient is in the least amount. So one hamburger requires 2 buns. So I got a top and bottom bun. Requires 1 patty. And however many slices of cheese you like to put on it. I like to have a little bit of cheese on mine, so I'm going to put 2. So I got a good deal of cheese on mine. So we know it requires 1 set of buns, 1 patty, 2 slices of cheese. Well, my least amount are the patties, the 6 patties. So I can only make 6 hamburgers because that is the least ingredient I have. Once I use these 6 patties and I use those 6 buns to go with it, and I use 12 pieces of cheese, I'm going to have left over 2 buns, 0 patties because I used them all, and 38 pieces of cheese. So my patties here were my limiting ingredient or my limiting reactant. I still got buns and cheese left over, but I don't have any patties left. So I can't make any more hamburgers. So hopefully that gives you an idea of what a limiting reactant is. And it all comes down to the balanced equation ratio once you get started. So just like stoichiometry, the best way to learn how to do this is just practice it. So let's just work through some practice problems and see if we can't figure it out. Now the key difference in these problems is you're going to have two masses or two quantities of substances or reactants. So instead of just having 1 mole of a substance or 1 mass of a substance, I got two. I got two quantities for my reactants. So it says how much water can be made from 2 moles of hydrogen and 3 moles of oxygen. So it says how much water. So we're looking for how much water can be made, and we're going to do it in moles since we are starting with moles. We'll just do a simple mole to mole conversion. It says I got 2 moles of hydrogen. So I got 2 moles of hydrogen gas. I got 3 moles of oxygen gas. All right. So my limiting reactant is going to determine how much of this water I can make. We got to figure out which one is the limiting reactant. To do that, we need to set up a proportion using dimensional analysis and the balanced equation. Doesn't matter which one you start with, just pick one. For this problem, I'm going to choose to start with oxygen. And the question I'm going to ask myself is how much hydrogen will I need to fully react 3 moles of oxygen? So let's set that up. I got 3 moles of oxygen. I put that over 1. Now, if I got 3 moles of oxygen and I'm trying to figure out how much hydrogen do I need, I got to convert moles of oxygen to moles of hydrogen. Since moles of oxygen is on top, I put moles of oxygen on bottom. Now I want to change it to moles of hydrogen so it goes on top. I need some values right here, so that's my balanced equation. There is 1 mole of oxygen for every 2 moles of hydrogen. So now we can do the math. So 3 times 2 is 6, divided by 1 is 6. So I need 6 moles. 6 moles of what? Well, H2 is the only thing left over. I need 6 moles of H2 to fully react 3 moles of O2. Well, if I need 6 moles of H2, how many do I have? Well, the problem says I have 2. I have 2 moles of H2. So I'm going to do a little less than or greater than comparison. Which value is bigger, 6 or 2? Well, 6 is greater than 2. So I need 6 moles of H2. I have 2 moles of H2. I don't have enough. I don't have all that I need. So H2 is my limiting reactant. And if H2 is my limiting, O2 is my excess. Or you can remember, if the left is larger, it's limiting. If this left value is larger, it's the limiting reactant. Left, larger, limiting. That's how I remember it. Alright, now that we know our limiting reactant, we can do our stoichiometry. So now it's just regular old stoichiometry like we've been doing. So since this is the excess, since O2 is the excess, I'm going to ignore it. I'm no longer using it. I'm only going to deal with hydrogen. And I want to figure out if I got 2 moles of hydrogen, how much water can I create? So let's figure that out. I got 2 moles of H2. Put that over 1. And I need to change that to moles of water. So I use the balanced equation. Moles of H2 is on top. Moles of H2 will go on bottom. I'm trying to change it to water. So moles of H2O go on top. Need some values. Now it's the balanced equation. There's 2 moles of hydrogen for every 2 moles of water. So I got 2 times 2 divided by 2 gives me 2. 2 what though? Well, moles of H2 canceled out, leaving me with moles of water. So I got 2 moles of water that will be produced from 2 moles of hydrogen and 3 moles of oxygen. And that is limiting reactants. So the only thing new here is this proportion set up here. That's the only thing that's new. And mathematically, it's the same as what you've been doing. You're just setting up some conversion factors. So hopefully that makes sense. But if it doesn't, let's try to do another one just to clear out any confusion. So next problem is how many grams of carbon dioxide will be produced from the combustion of 50 grams of propane and 75 grams of oxygen. Then we also got the question how many moles of the excess reactant will remain. So let's see if we can't figure this one out. So first thing we got to do is pick out that information. Let's pick out what's important. So it says how many grams of carbon dioxide. So I'm looking for CO2 and I'm going to try to convert it to grams at the end. I got 50 grams of propane and 75 grams of oxygen. So let's deal with this first question to begin with. How many grams of carbon dioxide will be produced? In order to figure that out, we got to figure out what's the limiting reactant. In order to do that, we need to know how many moles do we have of each, because we can't compare masses. Do a quick mole conversion for each of them. I got 50 grams of propane, and I need to know how many moles is that. So let's just do a simple mole conversion. Grams are now going to be on bottom, since grams were on top, and I'm going to change it to moles. So 1 mole of propane is how many grams? So let's use our periodic table in our calculator. I am going to round my molar masses to the nearest whole number. So carbon is 12, there's 3 of them. Hydrogen is 1, there's 8 of them. So that gives me a total of 44 grams per mole. So 50 divided by 44, I get 1.14. I got 1.14 moles of propane. It's moles of propane because grams of propane canceled out. Let's do the next one. Let's convert 75 grams of oxygen to moles. So I got 75 grams of oxygen. I put that over 1. Set up my ratio. 1 mole of oxygen is 32 grams for oxygen. So 75 divided by 32 is 2.34. 2.34 moles of oxygen. It's moles because grams canceled out. Now I definitely have more moles of oxygen than I do propane, but that does not mean it's the limiting reactant, nor does it mean it's the excess. The balanced equation tells us that. So let's look at that real quick. I need 1 mole of propane for every 5 moles of oxygen. I need 5 times the amount of oxygen in propane. Well, if I got 1 mole of propane, that means I need at least 5 moles of oxygen, and I clearly don't have that. So I'm taking a guess that this oxygen is my limiting reactant. But let's do the math and check it just to make sure. So let's figure out the limiting reactant. I need to know how much propane do I need to fully react 2.34 moles of oxygen. Let's set that analysis up. So I got 2.34 moles of oxygen, and I'm trying to figure out how much propane do I need. So if I got oxygen and I want to change to propane, I set up my dimensional analysis. Moles of O2 is on top. I put moles of O2 on bottom, moles of propane on top. Well, what's our balanced equation? There is 1 propane for every 5 oxygen. So 1 propane for every 5 oxygen. Moles of O2 will cancel out in this. So I do 2.34 times 1 divided by 5, and we get 0.47 moles. And that's going to be moles of propane. So this is how much I need in this reaction. How much do I have? Well, that's 1.14 moles of propane. I need 0.47 moles. I have 1.14. Which number is larger, 0.47 or 1.14? Well, that's 1.14. I have enough. So propane is my excess reactant. And if propane is my excess reactant, oxygen has to be my limiting reactant. So all my stoichiometry from this point on will be done using the moles of oxygen. So let's do that now. Let's figure out how many grams of carbon dioxide we will produce using our moles of oxygen, our 2.34 moles of oxygen. Slide down, make some more room. So I got 2.34 moles of oxygen, and I want to convert that to grams of carbon dioxide. So if I want to convert moles of oxygen to moles of carbon dioxide, we set up a proportion. So moles of O2 go on bottom, moles of CO2 go on top. Well, what's the moles for each? So let's look at our balanced equation. There are 5 moles of oxygen for every 3 moles of CO2. There are 5 moles of oxygen for every 3 moles CO2. Then once we get that converted, we want to change moles of CO2 to grams of CO2. So we can put that in our equation as well. So we don't got to stop. Since moles of CO2 is on top, moles of CO2 go on bottom, grams of CO2 goes on top. So 1 mole of CO2 is equal to 44 grams. I use my periodic table to add those atomic masses up. So moles of O2 will cancel out, moles of CO2 will cancel out, leaving me grams of CO2 for my answer. So let's do that math. So 2.34 times 3 gives me 7.02 divided by 5. I get 1.404 times 44 divided by 1, and I get 61.78. 61.78 what? Grams of CO2. So there is our first answer. But we had a second question we needed to answer. Let's look at that. How many moles of the excess reactant will remain? Well, it's not too difficult. We just got to figure out how many moles of the excess will we need. We already have that work done. We have it right here. Here's our need. Here's our have. So if we have 1.14 moles of oxygen, and I need, or to say I'm going to use 0.47 moles, how many will be left? So let's try to do that real quick. If I have 1.14 moles and I'm going to use 0.47 moles, how much will be left over? All you got to do is subtract right there. So 1.14 minus 0.47 leaves us with 0.67 moles of oxygen left over. So there is our second answer. So that is limiting reactants. The only thing new here is doing a conversion factor between your two reactants to figure out how much you need versus how much you have. So you do your mole conversions like you always do. Then you compare how many moles you have of each using your balanced equation. And that equation will tell you how much you need versus how much you have. If the left number is larger, it's limiting. Left, larger, limiting. If the right number is larger, it's excess. And then once you know you're limiting, your stoichiometry from there is the same as it always has been. And just like with the previous lesson, practice it till you can't miss it anymore. Just practice, 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 and you'll have this in the bag just the same as any other chemistry. I hope this video helps, and as always, good luck on your tests.